All right, so we have a few loose ends to tie up with regards to determinants. Let me mention this. We can find determinants of 2 by 2s and 3 by 3s by hand with only a reasonable amount of difficulty. 2 by 2s are super easy by hand. 3 by 3s are actually doable by hand as well. But beyond that, we're going to use technology. Okay, but I do want to show you how maybe an easier way to find the determinants of 3 by 3s that doesn't require the cofactor expansion. It's kind of a formula, but it's more of a process actually that can kind of be useful to know. Now, this is not in the book, so you'll want to just maybe keep this for reference. Here's a 3 by 3 matrix, A, B, C, D, E, F, G, H, I, and here is actually the formula for the determinant. Okay. Now, obviously, that's not as simple as the determinant or the formula we have for 2 by 2 matrices, but it exists. But I would not mess with remembering it or even writing down the formula. Instead, I want to let me show you the process that you'll use to find the determinant of a 3 by 3 matrix. It's actually the process I used to come up with this formula, and this formula is not something that usually finds its way into any math books. Rather, we have this process. So in short, if you have a 3 by 3 matrix and you need to find the determinant by hand, you can use the cofactor expansion, but generally the method that I use is this method right here. So there's my 3 by 3 matrix. If I want to find the determinant, I'm going to copy it down. And then what I'm going to do is I'm going to copy the first two columns. 7, 9, 4, 6, negative 3, 5 right next to it. Okay? And the reason I like this procedure is because it's kind of reminiscent of what we use with 2 by 2 matrices. So here's how it goes. You first start in this upper left hand corner, and you're going to multiply down that diagonal. Just multiply those three things. So let's put those in black. So 7 times negative 3 times 0 is of course 0. Okay. Then you're going to move over and multiply down that diagonal. 6 times 2 times 4 is 48. We're going to end up adding that to our previous result. And then we're going to multiply down this diagonal. Of course, that product is also going to be 0. Just for reference, AEI, BFG, and CDH are these three upper left to lower right diagonals. Boom. There, and there. If you were to write it out. Okay, but again, you don't have to remember this. Just use this. Multiply down the three main diagonals, get three numbers, add those together, and of course you get a 48. Now what we're going to do is we're going to go down the opposite direction. We're going to go down this diagonal and multiply those three together. When we do that, we get a 0. Then we'll move over, multiply down this diagonal. 7 times 2 times 5 is 70. And then we're going to multiply down this diagonal, which is another 0. We're fortunate to get a bunch of zeros here. Plus 0. And then we add those together, we get 70. Now we're not done yet, because what we do is we now take our first number, 48, minus our second number, and there we go. We get a negative 22 as our determinant. Okay, so that gives you a quick way to find fairly quick way to find determinants of 3 by 3 matrices, not using technology. Okay, now if you're going to use technology, both the TI calculator can find the determinant of a matrix. You just go into the matrix menu and find the determinant command, and GeoGebra can do that as well. I think you're just going to type in determinant into the input bar, and it'll ask which matrix you want to find the determinant of. Okay. Now let me just remind you real quickly. One of the things that now that we've spent some time finding determinants, we might have lost the reason why we're doing this. Determinants serve two purposes, at least at this point. Number one, we can use them along with Cramer's rule to find solutions to systems. And number two, if the determinant is 0, the matrix does not have an inverse. Okay, so that's kind of important. All right, that's kind of important. So if we're solving a system, we need the inverse to exist in order for us to have a single solution. All right, if it doesn't exist, then the system has no solutions. Or if the inverse doesn't exist, because the determinant equals 0, then the solution will not have a system. The system will not have a solution. Let's try that. Properties of determinants. Okay, just a few things to keep in mind. Remember, determinants come from matrices. And matrices we are always fiddling with as we reduce them, as we use Gauss-Jordan reduction. So and of course, to reduce them, we use our elementary row operations. We swap rows and we multiply rows by a constant, and then we multiply rows and add them. Okay, and so those 3 elementary row operations, each time we do one of those, we end up with a new matrix that looks different, but remember, it's an equivalent matrix, so that means the solutions are the same. So the question we might have is, if I take a matrix which has a determinant, say, of 22 or negative 22, and I perform a simple elementary row operation on it, how does that affect the determinant? Does the determinant stay unchanged, or does it change in a predictable way? All right, so let's talk about the 3 elementary row operations and how they affect our matrices. So, first operation. Let's try this. First operation is just swapping rows. Right? Seems super simple. It seems like it shouldn't change the determinant at all. But in fact, what does it do? It changes the sign of the determinant. So, like in our previous case, if I were to swap this row and this row, and get a new matrix, right? The new matrix would have a determinant of 22. And then if I swap again, it goes back to negative 22. That seems, that's a pretty big change for a simple little operation, right? But that is important to remember. Anytime you swap rows, you change the sign of the determinant, okay? The next most basic is if you multiply a row by a constant. Say k, right? So you just take this row and multiply by 7. You're not adding it and replacing it, you're just multiplying by 7. And we do that a lot. We actually do that a lot when we are creating ones, right? Like for instance, if I wanted this to be a 1, I would multiply by 1/9, right? So my k would be 1/9. So the question is, what happens when you multiply by a constant? Well, the new determinant is also multiplied. Let's write it like this. Well, what happens is you will multiply the determinant by k as well. Let's write it like that. So if I were to multiply this row by 15 for some reason, I don't know. No, let's go 3. If I were to multiply that row by 3, so it'd be 21, 18, and 0, and then found the determinant of that new matrix, it would be negative 66. I would just take the old determinant and multiply it by 3 as well. Okay, so those are pretty basic. Okay, our most complicated operation is to multiply a row by k and add to another row, right? That's the one that seems like it's the most, destructive, or the one that changes things the most, right? That's the one we use all the time to eliminate things, right? Um, so if I were to do that, you would think the determinant would change, but in fact, there is no change. The determinant remains unchanged. Okay. Now that's it. That's don't disappear. There's no change to the determinant. Now, again, that's supposing I only multiply one row and add it to another row. Okay. If I multiply two rows, say for instance, like if I were working with this matrix and I wanted to eliminate this term, right? I would multiply this row by a -9. I would multiply this row by a 7, and then I would add, right? And replace this row. Okay, I've actually done two operations there, right? The first operation was to multiply that row by 7, and that's going to multiply the entire determinant by 7. The second operation was to multiply this by -9 and then add and replace. That's not going to change. Okay, so if all I do is multiply one row and add to another, then there is no change. But if I end up multiplying two rows, then the row that gets replaced, whatever I multiplied it by to line things up, will also multiply the determinant. That constant will multiply the determinant. You can check that out and see that those things happen.